Effect of negative feedback. Effect of parameter variation reduces the gain of system reduces by a factor 1 by a factor 1 plus gh. The bandwidth of the system increases. Effect of internal disturbance reduces. Comparison of open loop and closed loop control systems. Open loop systems, as long as the calibration is good, open loop systems will be accurate. Organization is simple and easy to construct, generally stable in operation. If non-linearity is present, system operation decreases. Whereas closed loop system, due to feedback, the closed loop system is more accurate, complicated and difficult. Stability depends on system components. Comparatively, the performance is better than open loop system if non-linearity is present. Tachometer is a speed transducer used as feedback element in control systems. Omega S, KT, E naught S, or theta of S, SKT, E naught of S. SKT is tachometer constant. Transfer function. The transfer function of a linear time invariant differential equation system is defined as the ratio of the Laplace transform of the output to the Laplace transform of the input. One of the assumptions that all conditions in all initial conditions are zero. G of S equal to L of Y of t by L of U of t, Y of S by U of S. The system is said to be linear if the principle of superposition, principle of homogeneity applies. A differential equation is linear if the coefficients are constants or function only of independent variables. Open loop transfer function. Transfer function C of S by R of S equal G of S, where C of S equal to Laplace transfer function of output. R of S is the Laplace transformation of input. Impulse response of a system G of t equal to C of t, where G of t impulse response, C of t output of the system. The transfer function of a system is the Laplace transform of its impulse response. Transfer function is always calculated with zero initial conditions. Transfer function Tf equal to G of S by 1 plus G of S H of S. Mason's gain formula P equal to 1 by delta sigma k pk delta k. P means overall gain or transfer function. Pk means path gain of the kth forward path. Delta means 1 minus sum of loop gains of all individual loops plus sum of gain product of all possible combinations of two non-touching loops minus sum of gain products of all possible combinations of three non-touching loops. Delta k, value of delta obtained by removing all the loops touching kth forward path. Forward path is a path that can be traced to the graph from the input node to the output node without touching a node twice. Path gain is the product of all branch gain in a path. The individual loop is a closed path starting and ending at the same node. Loop gain is the product of all branch gains in the loop. Non-touching loops are loops which do not have a common mode. Sensitivity. Sensitivity equal percentage change in A by percentage change in K. S A K equal dou A by dou K by K. Dou A by dou K into K by A, where SKA, sensitivity of variable A with respect to parameter K. Sensitivity of overall transfer function M of S with respect to forward path transfer function G of S for open loop control systems. SMG equal to G of S by M of S into dou M of S by dou G of S equal to 1. For closed loop control systems, SMG equal to 1 by 1 plus G of S H of S. Sensitivity of overall transfer function M of S with respect to feedback. Path transfer function H of S equal HS. SHM equal G of S H of S by 1 plus G of S H of S. Closed loop system is less sensitive to parameter variation, hence closed loop system is better. Time response analysis of control systems. Time response of a control systems means as to how a system behaves in accordance with time when a specific input signal is applied. Transient response, steady state response. Transient part of the time response reveals the nature of the response and its speed, whereas steady state part of the response reveals the accuracy of a control system. Step function. R of t equal to a into u of t equal to 1 for t greater than equal to 0, 0 for t less than 0. Ramp function, R of t equal to a t, t greater than equal to 0, 0, t less than 0. Parabolic function, a t square by 2, t greater than 0. Impulse function, a and L of t, a, t equal to 0. Limit alpha tends to 0, minus alpha to alpha del of t dt equal to 1. Time response of a first order control system. Transfer control function, C of S is R of S equal to 1 by S tau plus 1. Response of unit impulse response function. Time response expression C of t equal to 1 by t e power minus t by capital T u of t. Response to unit step function. C of S equal to 1 by S into S tau plus 1. Time response expression C of t equal to Laplace inverse of C of S equal to 1 minus e power minus t by tau u of t. Error e of t equal to R of t minus C of t equal to e power minus t by tau u of t. Steady state error ES is equal to limit t tends to infinity e power minus t by tau equal to 0. Lower the time constant, faster is the time response of a control system. Response to unit ramp input function. Response to unit ramp input function Time response expression C of t equal to t minus t plus t into e power minus t by t u of t. Here e of t equal to r of t minus e of t capital T minus capital T into e power minus small t by capital T into u of t 1 minus e power minus t by t u of t. Steady state error ES is equal to limit t tends to infinity t minus t into e power minus t by tau equal to t. Time response to unit ramp input function. Okay, now time response of second order control systems. The g of s is nothing but omega n square by s into s plus 2 zeta omega n. Then transfer functions u of s by r of s equal to omega n square by s square plus 2 zeta omega ns omega n square, where omega n means natural frequency of oscillations, zeta means damping ratio, zeta omega n means damping factor, damper frequency, omega d equal to omega n into root of 1 minus zeta square, where omega d equal to damper frequency of oscillations. Response to unit step input function, time response expression, case 1, zeta equal to less than 1, that is under damped oscillations, c of t equal to 1 minus e power minus zeta omega nt by root of 1 minus zeta square sin omega dt plus 5 u of t, where phi equal to tan inverse of root over 1 minus zeta square by zeta. Response settles within 2% of the desired value of 1 unit of damping out of the oscillations in a time of 4t or 4 by zeta omega n. 4 by zeta omega n. 2 zeta equal to 0, that is sustained undamped oscillations c of t equal to 1 minus cos of omega n t u of t. Case 3 zeta equal to 1, that is critically damped oscillations c of t equal to 1 minus e power minus omega nt into 1 plus omega nt. Case 4 zeta greater than 1, that is overdamped oscillations c of t equal to 1 minus e power minus half 1 zeta minus root over zeta square minus 1 omega nt by 2 into root over zeta square minus 1 into zeta minus root over zeta square minus 1. Effect of zeta on time response. Value of x zeta equal to 0. Type of closed pose purely imaginary. Nature of response oscillations with zeta constant frequency and amplitude. System classification comes as undamped. Whereas 0 less than zeta less than 1, complex conjugate poles. Some types of closed poles becomes complex conjugate. Nature of response becomes damped oscillations, and system classification comes under damped, where zeta equal to 1, that is very system classification is critically damped. The type of closed poles becomes real, equal, and negative. Nature of response is considered as critical and pure exponential, whereas 1 less than zeta less than infinity type of closed poles are real, unequal, and negative. Nature of response purely exponential, sluggish and slow. Slow and sluggish system classifications is called as overdamped. All zeta increases from 0 to 1, then the frequency of oscillation reduces. For all positive values of zeta, systems are stable. Pole away from the origin are called insignificant pole and does not affect the stability of system. Theta equal to cos inverse of zeta. Some practical example of signal system. Series RL circuit characteristic equation S square plus R by LS plus 1 by LC equal to 0. Parallel RL circuit characteristic equation S square plus 1 by RC S plus 1 by LC equal to 0. Translator system characteristic equation S square plus F by MS plus K by M equal to 0. Rotational system S square plus F by JS plus K by J equal to 0. The series RL circuit లో omega n equal to 1 by root LC, zeta equal to R by 2 into root over C by L. The parallel RL circuit లో అయితే omega n equal to 1 by root LC, where zeta equal to 1 by 2R into root over L by C. The translator system లో zeta equal to F by 2 root Km. Rotation system లో zeta equal to F by root Kj. Transient response specifications of second order control system. Peak overshoot, TD, TR, TP, TS. Delay time. It is the time required for the response to rise from 0 to 50%. The final value Td equal to 1 plus zero point 0.7 zeta by omega n. Rise time Tr is the time required for the response to rise from 0 to 100%. It's damped 5 to 95%, critically damped 10 to 90%, over damped of the final value. So equation T R equal to pi minus tan inverse root over 1 minus zeta square by zeta whole by omega d, that equal to pi minus cos inverse zeta by omega d. Peak time Tp, it is the time required for the response to rise from 0 to peak of the time response. Tp equal to n pi by omega d, where n equal to 1, 2, 3. N tends to 1, first peak overshoot. N tends to 2, first undershoot. Settling time Ts, it is the time required for response to rise and reach to the tolerance band. For 2% tolerance band, Ts equal to 4, T equal to 4 by zeta omega n. For 5% tolerance band, Ts equal to 3, tau equal to 3 by zeta omega n. Then peak overshoot Mp, it gives the normalized difference between the steady state output to the first peak of the time response. Percentage of Mp equal to e power minus pi zeta by root of 1 minus zeta square into 100%. E power minus pi zeta by root of 1 minus zeta square into 100%. Time period of oscillations before reaching the steady state T oscillation equal to 2 pi by omega d, number of cycles before reaching steady state n equal to T settling by T oscillation. Type and order of system. Every transfer function represented in the control system has certain type and order. The steady state analysis depends on the type of the system. The type of the system is obtained from open loop transfer function, that is G of s into H of s. The number of open loop poles occurring at origin determines the type of the system, that is G of s H of s equal to k into 1 plus sta by s power d into 1 plus st1. P equal to 0 for type 0 system, P equal to 1 for type 1 system, P equal to n for type n system. Transient steady state analysis depends on order of the system. The order of the system is obtained from closed loop transfer function, that is g of s by 1 plus g of s h of s. The highest power of characteristic equation, that is 1 plus g of s h of s equal to 0, determines the order of the control system. Steady state error E of s equal to R of s by 1 plus g of s h of s. Steady state error ESS equal limit t tends to infinity E of t in time domain. ESS equal limit s tends to 0 s into E of s in s domain. Steady state error ESS equal limit s tends to 0 s into R of s by 1 plus g of s h of s. Steady state error depends on the two factors: type of input applied, that is R of s; type of system, that is G of s h of s. Steady state errors for different types of input. Step input R of s equal to a by s. ESS equal to a by 1 plus kp, where kp equal to limit s tends to 0 g of s h of s, where kp is static position error constant. Ramp input R of s equal to a by s square, ESS equal to a by kv, kv equal to limit s tends to 0 s into g of s h of s, where kv means static velocity error constant. Parabolic input R of s equal to a by s cube, ESS equal to a by ka, ka equal to limit s tends to 0 s square g of s h of s, where ka means static acceleration error constant. For step input, steady state error for different types of systems. Type 0 means step input a by 1 plus k. Type 1 step input 0. Type 2 step input 0. For type 0 ramp input infinite. Type 1 ramp input a by k. Type 2 ramp input 0. Type 0 parabolic input infinite. Type 1 parabolic input infinite. Type 2 parabolic input a by k, where k is the system gain. Steady state error ESS is directly proportional to 1 by k, so as system gain increases, steady state error decreases. For linear time invariant LTE system, the maximum type number is 2. Beyond type 2, the system exhibits non-linear characteristics. Steady state error is valid only for a closed loop system stable. System steady state errors are calculated for the closed loop system by using open loop transfer function. Stability of time domain. Stability, linear time invariant system is said to be stable if the following conditions are classified. If the system is excited by a bounded input, the output must be bounded. If the input to a system is 0, the output must be 0 irrespective of the initial conditions. Marginal stable system. A LTE system is said to be marginal stable if the bounded input, the output maintains the constant amplitude and frequency. Absolute stable system. System is stable for all the values of system k in k from 0 to infinite. Conditional stable system. System is stable for certain range of k. Routh-Hurwitz criterion. Purpose: to find closed loop system stability. Number of closed loop pole in right side or left side of the S-plane. Range of k for conditionally stable system. Value of k required for marginal stability, and thereby determining the frequency of oscillations. To find a closed loop system stability by using RS criteria, we need characteristic equation, that is 1 plus g of s h of s equals 0. Router generally nth order characteristic equation is a naught s power n plus a1 s power n minus 1 plus a2 s power n minus 2 plus and so on. A n minus 1 s power 1 plus a n equals 0.